right, we're going to be doing a chapter 6 uh, homework uh, examples. We're going to start with a little cheat sheet that I'll pass this out to you, and it's these are formulas for momentum. Now, momentum, which we define, we assign the letter P to momentum. Momentum is equal to mass times the velocity. So if you have mass in kilograms and velocity in meters per second, your momentum is going to be kilogram meters per second. That's how we define it. So if I ask you to find the momentum of a football player running so many meters per second, you just multiply his mass by his meters per second, you get his momentum. Impulse is equal to force times time. Impulse is equal to force times time. And we learned that impulse causes a change in momentum. The delta means change, so impulse is equal to delta mv. Now, most of the time, m is going to stay the same, and your velocity is what changes. But there are instances where mass does change. You think about a rocket that's expelling fuel. Its mass is changing over time. But for our purposes, we're going to stick with the mass being constant and only the velocity changing. So if impulse is equal to force times time, and impulse causes a change in momentum, then force times time equals a change in momentum. Now, we can write that alternately as force is equal to delta mv, change in momentum, divided by time. And if you recall, if we can increase the time, since force is inversely proportional to the time, since the time is in the denominator, if we can increase the time, we decrease the force. If we increase the time, you decrease the force. If you decrease the time, you increase the force. Okay, now, these are some conservation of momentum rules that we're going to study. The total momentum before equals the total momentum after. So mv before equals mv after. Now, that mv may be a combination of things. It could be like a cannon and a cannonball. Before it's fired, you have the mass times the velocity of the cannon plus the mass times the velocity of the cannonball. Well, both of them, before it's fired, they're zero. So the total momentum before is equal to zero, and the momentum afterward has to be zero. So you have the cannonball moving after it's fired. The cannonball moves at a certain velocity, and it has mass, and the cannon has mass and is moving in the opposite direction, so that they're going to cancel. So our total momentum afterwards is going to be zero also. And then we're going to talk about elastic collisions. M1 V1 plus M2 V2 before has to equal M1 V1 plus M2 V2 afterward. A lot of times let's say V2 is equal to zero. You have a little car running into a stationary object. So the V2 is zero, and there's going to be a change afterwards, but the total momentum before has to equal the total momentum afterwards. Now, in elastic collisions, where we remember the Walter Fent little demonstration, the two little train cars were coupled, so that's what an inelastic collision is. The things adhere one to the other. So M1 V1 plus M2 V2 is going to equal the combined masses M1 plus M2 times the V total. There is no V1, there is no V2. It's the V total. It's a new velocity of the cars. Okay, and that's it for the cheat sheet. Now let's do some examples. Let's do a new share and go to the iPad. And let's see. And there it is. I'm going to go ahead and dismiss my image. I don't think you need to see me. Here's a repeat on these are the same equations I just discussed. Now, what is the momentum of a 9-kilogram bowling ball rolling at 2 meters per second? Well, momentum is equal to mv, so that's 9 kilograms times 2 meters per second. That's equal to 18 kilograms. I almost forgot to write 18 kilogram meters per second. That's it. That's the answer. 18 kilogram meters per second. Okay? What impulse occurs when an average force of 10 newtons is exerted on a cart for 3 seconds? Okay? Impulse equals force times time. And so we get 10 newtons times 3 seconds. So you get 30 Newton seconds. Okay? All right. What is the impulse on a 9-kilogram ball rolling at 2 meters per second when it bumps into a basket and stops? Okay, so the impulse is equal to delta mv. And in this case, it's going to be the v that changes. So that's equal to m delta v, which is equal to the mass times final velocity minus initial velocity. So let's rewrite it down here. The mass is 9 kilograms, and that's multiplied by, well, what is the final velocity? Well, it comes to a stop. So that's 0 meters per second minus 2 meters, 2 meters per second. So that's 9 kilograms times a minus 2 meters per second. And that's equal to minus 18 kilogram meters per second. That's the impulse. Okay? All right. Now, this is going to be a conservation of momentum problem. So we're going to use M1 V1, oops, not VI, M1 V1 plus M2 V2 initial equals M1 V1 plus M2 V2. Actually, let me back off on that one because it is notice that it says the two stuck together blobs. So we've got M1 plus M2 equals, not equals, times a new velocity. Okay, so M1 is 2 kilograms times a velocity of 3 meters per second plus M2, which is the same thing, 2 kilograms times 0 meters per second. So this whole thing is 0, and it's going to equal M1, M2, so that's 2 kilograms plus 2 kilograms times some final velocity. Oh, okay. They give us the answer, 1.5, and we're going to show you how to get it. Okay. So that ends up 2 kilograms times 3 meters per second equals 4 kilograms times V. And now we need to find V. Well, to find V, we divide both sides by 4 kilograms. So this is 2 kilograms divided by 4 kilograms times 3 meters per second. Well, that's 1/2. 2 over 4 is 1/2. And so 1/2 of 3 is 1.5 meters per second. And there's our answer. That's how we got it. Okay? Okay. Lil drives her car with a mass of 1,000 kilograms at a speed of 20 meters per second. Show that to bring her car to a halt in 10 seconds, in 10 seconds, road friction must exert a force of 2,000 newtons on the car. Well, let's say we don't know what that is. We don't know what the force is, but we know that force times time is equal to the change in momentum, delta mv. So we're going to find that the force is equal to delta mv divided by the time. Okay, and that's going to equal m times v final minus v initial divided by the time. Okay, so force is equal to the mass is 1,000 kilograms. And what is her final velocity? Her final velocity is 0. It says to bring her car to a halt. So that's 0 meters per second minus 20 meters per second divided by 10 seconds. So the force is equal to 1,000 kilograms times minus 20 meters per second divided by 10 meters per second. And that's it. So that's equal to 2. And the force is actually, because it's a negative force to bring it to a halt, it's equal to minus 2,000. Let's see, I wrote this wrong. Let me erase this. This is meters per second divided by second. So that's meters per second squared. So it's 2,000 kilogram meters per second squared. Well, what is that? That is 2,000 newtons. It's really minus 2,000 newtons. Is that what it says in the, no, it just says 2,000 newtons. They're ignoring the braking force, but it is negative to stop the car, stop the vehicle. Okay. Now this is one where it's non-linear. You have 2 automobiles, each of mass 10,000 kilograms, not 10,000, 1,000 kilograms, are moving at the same speed, 20 meters per second. When they collide and stick together, cite the direction and speed of the wreckage. Cite the direction and speed the wreckage moves when one car was driving north and one south. Okay, so I'm assuming that if that's the case, they're headed towards one another. Okay, each of mass 1,000, and they both have the same speed. So this momentum will make up positive and down negative. So this is 1,000 kilograms times, what was it, 20 meters per second. That's and I said downward was negative, so we're going to make this a minus 20 meters per second because it's downward. So this is 20 minus 20,000 kilogram meters per second. And this is 1,000 kilograms times 20 meters per second in the upward direction. So that's equal to 20 kilogram meters per second. Well, the total momentum afterwards is going to be 20,000 kilogram meters per second minus 20,000 kilogram meters per second. And that's going to equal 0 kilogram meters per second. Okay. Now, part B, one car was driving north and one east. The way it shows in the little figure. And they even give us the hint. It looks like it's going to be going 45 degrees, but it's going the resultant is going to be, let's draw a little diagram. The resultant is going to be, this is 45. Oops. 45 degrees. So the resultant is going to be the square root of 20,000 kilogram meters per second squared plus 20,000 kilogram meters per second squared. Let's extend our little line here. And that's going to be the same as R equals 20,000 times the square root of 2, or 1.414 kilogram meters per second. And let me pull out my little calculator. So 2 square root of 2 is 1.1412, 1.4142, and multiply that by 20,000, and it's 28,284. Probably 28,000 would be a good enough answer. Kilogram meters per second, and the direction is going to be northeast, 45 degrees. Okay, I thought there was more problems, but I think that's enough to give you some experience in doing these problems. Okay, I think with that we'll end the lecture. Okay.